Okay, thank you, Joe. So I would like to start by thanking the organizers for the opportunity to present this work here and for organizing this very nice workshop. So my talk will be about Lifshitz Holography, and this is a work that is to appear soon and that I did together with Morten Christensen, who recently got his master degree at the NBI, Niels Obers and Blaise Royer, who is here in the audience. So to give you an outline of my talk, I will start with a motivation why I'm interested in Lifshitz holography, and then I will introduce the specific model that we use and discuss some basic properties of Lifshitz solutions. And then I will introduce the notions of doing holography. You want to go beyond this, so you introduce the notion of asymptotically locally Lifshitz. Turns out that those are not the most general solutions of the equations of motion, so there is a notion of going beyond that, which will then lead me to discuss asymptotics. And then finally, sort of the first real question of this research, what is the boundary geometry that you want to associate with Lifshitz holography? And I will try to convince you that this is described by Newton-Cartan geometry or some generalization thereof. And then we have all the tools to study covariant identities for the ward identities. This will involve identifying all the sources in the theory, the local symmetries acting on them, and then we can compute the boundary stress tensor. And then I will show you some kind of counting argument, how many sources and veps there are in the theory, and then you can ask a basic question. If I'm giving this boundary data, can I holographically reconstruct the spacetime like you can in ADS? And I will show you that this is not so straightforward. And then I will conclude with a summary and outlook. So Lifshitz holography is interesting for a number of reasons. One of them being that this is an explicit example of a non-asymptotically ADS space. And if you ask yourself the general question, how general is holography, then Lifshitz is a very specific case where you can sort of ask this question directly, and you can also ask the questions of how holographic are they? So what are the necessary geometrical objects involved, and how to do holographic renormalization and all these things. They also naturally appear in the context of ADS-CMT as infrared geometries, as we saw in many talks in this conference before, and where they can be also hyperscaling violating. Those are conformally Lifshitz, but for the purpose of holographic renormalization, it's really the dynamical critical exponent which introduces complications, not so much this hyperscaling violation. That's just a conformal transformation that you could deal with once you know how to do it for Lifshitz. I'm pretty confident you can do it for hyperscaling as well. So more specifically for this talk, we're interested in identifying the boundary geometry, being able to compute boundary stress tensors, identifying the most general solution of the equations of motion, and then this final question, what about holographic reconstruction, once I have all the sources and the veps. Okay, the model that we're going to be using is very specific. You can get it from a reduction of type 2B supergravity, where you only keep the metric and the axion dilaton system. So this is the same kind of thing that would sort of give you the near horizon geometry of the free branes. And if you further reduce this down to 4 dimensions, Lifshitz solutions are typically solutions of theories with massive vector fields. And one way to get a massive vector field is to do something that's called a Shirk-Schwarz reduction. So you take this axionic field and you give it a linear momentum in the compact coordinate. And this, what this does is that you're going to gauge the axion shift symmetry with the Kaluza-Klein vector. And that introduces this gauge covariant derivative here, which you can interpret, which is given here, which you can interpret as a mass for the gauge field. So this is one way to get massive vector fields from dimensional reduction. And it also adds another term to the potential. So this is our 4-dimensional model that has Lifshitz solutions. But what the main reason that this is an interesting case is that all Lifshitz things over here, so this reduction is consistent. So all solutions to the equations of motion here are solutions to the equations of motion there. And what is Lifshitz over here uplifts to something that is ADS in 5 dimensions. And in 5 dimensions, for asymptotically ADS spaces, you know very well how to do holographic renormalization. In fact, for this model, that has been worked out by Papadimitriou. And then you can just reduce all the counter terms, and then you get the counter terms for this action. You can reduce the Pfefferman-Graham expansion, all these things. So what this model buys you is that you can you get everything by reduction. Whereas if you would take a phenomenological model, in principle you don't know what the most general solution to the equations of motion is. Okay, so this four-dimensional model has this particular Lifshitz solution. It only has a z2, so this parameter we cannot play with, it's fixed. So we have this 1 over r to the 4 term in the metric. This is the most dominant term. I've introduced here the ADS length only for this slide, but in the rest of the talk it will be 1. The Klooster-Klein dilaton is constant because it's Lifshitz scale invariant, and it's basically given by the string coupling. This is e to the phi. And if you uplift this metric to 5 dimensions, you see it is asymptotically ADS. So this is the leading piece, this is of course ADS. And then you have this sub-leading term there. That sub-leading term is very important because this is the compact coordinate, and this is what makes the circle space-like everywhere in the bulk. So from a boundary perspective, this is actually a null circle that's going to play an important role. But everywhere in the bulk, you can compute the size of the circle. So it has a physical radius given by this formula here, which is just basically given by the periodicity of the u coordinate and the string coupling. And then in order for this to be a good approximation, you make the usual assumptions that the ADS radius is much larger than the string length, you are at weak coupling, and now you also impose that the length of this, that the circle is much larger than the typical length of a string, and you can very easily account for those inequalities. And in fact, on top of this, you can furthermore look at 3 different regimes where you compare the compactification with respect to the ADS radius. And when this is much larger than 1, you are in a decompactification regime. The boundary theory is then NS4 Cyprian-Mills, of course, in the background of an axion field. And when it's much smaller than 1, you can consistently decouple the Klooster-Klein modes, and you get a 3-dimensional theory where the 3-dimensional boundary has been dubbed some Lifshitz Chern-Simons gauge theory in this paper here. And if you're in the middle of this, you have some discrete light cone quantization, but in the presence of a non-zero theta angle. Okay, so this is a good approximation. The reduction is consistent, and now we can sort of start to ask some holographic questions. So the first thing is to introduce more solutions. So asymptotically locally Lifshitz, as was introduced by Ross. I'm working in a different gauge, so I don't have radial gauge in 4. I have radial gauge in 5 dimensions, but that's just a technicality. The main point is still the same. So I take now a Vielbein basis, and I'm going to take the time-like Vielbein to blow up faster than the space-like ones. This is exactly this critical exponent z here, equal to 2. And then these are going to be the boundary frame fields, and this boundary frame field has to be hypersurface orthogonal for this to be asymptotically locally Lifshitz. That means that you have some notion of absolute simultaneity in this boundary theory. And there is furthermore some technical requirement that these scalars are asymptotically constant related in this way. This is because of this non-radial gauge. If you want to transform to radial gauge, and these are asymptotically constant, you can actually see that the leading behavior of the metric is 1 over r to the 4 as required here. But apart from this, the boundary gauge field and the boundary axion are completely arbitrary. Where note, by the way, that the boundary gauge field is defined, is not the leading component of the massive vector. You have to subtract off this time-like Vielbein here, and it's the leading component of this combination. If on top of this being hypersurface orthogonal, you assume that it has no curl, then you don't only have surfaces of absolute simultaneity, but you have an absolute time, as we will see later. And then what happens is that the metric is asymptotically scale invariant. So then you recover asymptotically scale invariant metrics. And this will play an important role later on. But you can immediately see that this definition is most likely not the most general thing, because you have quite a number of assumptions here. This hypersurface orthogonality condition, asymptotically constancy condition. So there are these deformations where you relax those conditions, and if you relax all of them, what happens is that equations of motion will not allow you to do that completely. They will always enforce one particular constraint. So we have one algebraic or almost algebraic constraint on these sources, but we can handle that. This is just a complication. Okay, so now we know what the most general solution is, because we get it from the reduction. And in this gauge, and that will allow us to identify what the boundary geometry is. So if we work in this gauge, then the fall off of the field lines is like this. This is the inverse field line. And then, of course, they have to satisfy these orthogonality relations. But please be careful that you should not think that you can raise and lower these indices, because it will turn out that there is no Lorentzian boundary metric. They are really independent quantities, apart from the fact that they have to satisfy these conditions. So to find out what kind of boundary geometry corresponds to these frame fields, one question you could ask yourself is, how do they transform? We know that these guys transform under local Lorentz transformations, but what is the effect of a local Lorentz transformation from the point of view of the boundary geometry? It turns out that you don't get Lorentz transformations on the boundary anymore, but you get something which is a contracted group. This is because these light cones, they flatten out because of the z equal to 2. And then if you work this out, it turns out that you get these particular transformations. So this one, for example, transforms under an SO2 rotation. This one is invariant. This is a Galilean boost, and this one has Galilean boosts and SO2 rotations in it. And then if you want to build a metric, they have to be invariant on these local tangent space group transformations. And then you can easily convince yourself that these are the only two invariant objects that you can define. But these are degenerate metrics. So this one has 2 0 eigenvalues, this one has 1 0 eigenvalue. Okay, so this is going to be some non-relativistic geometry, and in order to identify what this geometry is, we need a connection. And there are in principle 4 different connections. You can define covariant derivatives by demanding that they transform covariantly in this way. So for example, I wrote down the covariant derivative for this field line here. And the field line postulate that we're going to impose is that this one vanishes. This is a good choice because it allows me to fix both these so-called spin connection coefficients, or what you would normally call the spin connection coefficient. But different from the Lorentzian case, this field line postulate does not completely constrain what you normally would call the Christoffel connection. It constrains it in the following way. So these two projectors on this covariant derivative, which only involves gamma, acting on this space-like metric, must vanish. But other than that, you're free to choose it as you like. And the choice we're going to make is sort of inspired by this null reduction on the boundary. If you take the connection of the ADS boundary metric and you only look at the directions, the non-compact directions, and you do that for the case for asymptotically locally Lifshitz spacetimes, this is what we are going to call our connection. If you relax the boundary conditions, you will get corrections here, but we will keep with this particular definition. So if you make this identification in this case, you get this particular expression, and in the most general case, we will keep with this connection here. And this already looks very much like this is going to be Newton-Cartan. In fact, so it has a time-like Einbein, the space field metric. This is a contribution from the boundary gauge field. And if you have furthermore this condition here, the boundary geometry is exactly Newton-Cartan in the sense that you have these sort of metric compatibility conditions. And so this is the case where the boundary geometry is going to be exactly Newton-Cartan. But we don't have this condition in general. In general, this combination is non-zero, and it turns out that this introduces torsion. So if you define these torsional derivatives, so you have these torsion components here, then in general, for the most general solutions to the equations of motion, the conditions are exactly given here. So in general, the boundary geometry is torsional Newton-Cartan. And then there is an in-between case where this is non-zero, but it's still hypersurface orthogonal that satisfies this condition here, and that's what we call twisted torsional Newton-Cartan, but never mind this case too much. The most important message is that you can have Newton-Cartan or torsional Newton-Cartan. So to summarize the boundary conditions, so the most restrictive case is that you have exactly asymptotically Lifshitz metrics. So here are the 3 conditions involved in these definitions. So you have hypersurface orthogonality is satisfied. This thing has a vanishing curl that's satisfied. That means that there's an absolute Galilean time. This is then the gradient of that absolute Galilean time. And this being constant means that the coordinate transformation to radial gauge is fairly straightforward, and you don't get any lock terms in the radial gauge metric. Then you can go to asymptotically locally Lifshitz by dropping this condition here. And the most extreme case is where you violate all of these conditions, and there the boundary geometry is torsional Newton-Cartan. So we have now identified what the boundary geometry is, and as well we have identified what are all the sources. So we have boundary frame fields, we saw a boundary axion, we have the boundary dilatons here, a boundary gauge field, which I remind you is the leading component of this combination. So now we can sort of ask the question, what are their dual vacuum expectation values? So what you would have to do is you take the 5-dimensional theory with the axion dilaton system, you add all the counter terms, and you reduce them to 4 dimensions. You put the whole, you compute the variation, you put the whole thing on shell. You can do all these things, and after a while, what you find is this particular on-shell variation of the 4-dimensional action. So here you have all the variations of the sources. I said in the beginning that there is a constraint on these sources. These variations must still sort of obey that constraint. I did not include it here because it's technical, but you can deal with it. It's not, but modulo that comment, I'm going to call this vacuum expectation values. And here you have what would be the Lifshitz scale anomaly, which I will discuss later. So here you see that in order to, so this is what's going to be the basic building blocks. So in front of the variations of the field lines are going to be the basic building blocks of the boundary stress energy tensor. So to compute water entities, we need to identify the local symmetries. So obviously we have diffeomorphisms. They are just Lie derivatives of these fields. I didn't write them down. You have now anisotropic Weyl transformations. So this is with a Z is 2 here, and also here for the time-like component. Then you have gauge transformations, you have local tangent space transformations. This is this contracted version of the Lorentz group. I didn't write them down here, they were on the previous slide. And there is an additional transformation, which is not obvious from what I told you. But if you look at the Pfefferman-Graham expansion in detail, you can see that this is a transformation that leaves the Pfefferman-Graham expansion invariant at leading order, but it's broken at subleading orders. However, that is still good enough to derive another ward identity because this only cares about what happens with the leading order terms. So I cannot remove a source, but I do get a ward identity. That will play a role later. So, as I said, these are the basic building blocks of the boundary stress tensor, but they are not gauge invariant. And you need to add these terms here to make them gauge invariant, where these guys are the, if I go back, are the variations in front of the flat indices. This is the boundary gauge field, but turned into a scalar here, and these quantities here appear in front of it. So that's what you need to add to make this gauge invariant. And then in order to make it also invariant on the local tangent space transformations, you add these particular frame fields in front of it. And then this object here is then what we call the boundary stress energy tensor. And note that it has one index up and one index down, and you cannot raise and lower indices because we don't have a Lorentzian metric. So this thing is a 1,1 tensor. So this is very different from what you have in relativistic cases like for example in ADS CFT, where the boundary stress energy tensor is a symmetric object with 2 indices down. So you can derive all the ward identities, and I've given here only a few of them. So if you, for simplicity, I assume that the boundary geometry is Newton-Cartan. And then if you look at the ward identities for diffeomorphisms, this is what you get for the divergence of this stress tensor. And notice that even if these boundary, oh yeah, by the way, this is a gauge invariant combination here. So this is sort of an, this is what you would call the boundary massive vector field. So these are all scalars. Even if I would turn them off, this thing would still not be conserved. And that's actually standard if you define stress energy tensors by varying with respect to field binds in the presence of vector fields. It's known from the work of these people that in general these boundary stress tensors are not conserved, and you get these kind of terms on the right hand side. So if you want to construct a conserved current, what you can do is you just contract this with a vector k, which is over here. You pull it through the derivative, you put everything else on the other side, and you demand that that vanishes, where you are allowed to use ward identities to put it to 0. And one very simple way of making that possible is just by demanding that these Lie derivatives are zero. This is by no means necessary. This is just a sufficiency condition. You can substantially relax this type of conditions. So this is kind of a sort of a notion of a killing vector with respect to Newton-Cartan geometry, which allows you then to write down these conserved currents. And if the boundary allows you to define this kind of vector fields, you would have sort of conserved energy flow, momentum flow, and everything as discussed in this paper. You also have a ward identity for the anisotropic Weil transformations, which gives you the Lifshitz scale anomaly, which is this term over here. And note here that you have these factors of 2, which is the critical exponent again. So what is this object? If you compute it for the most general, or for the most restrictive boundary conditions, which is exactly asymptotically Lifshitz, this is just a normalization, but you get this expression over here. And you may recognize, so this is some fourth order derivative term, and each of these terms are separately invariant under anisotropic Weil rescalings. And it's quite amusing that this takes, this term you can forget about. But it's quite amusing that this is exactly the form of a Horava-Lifshitz action. So the Lifshitz scale anomaly is described by a Horava-Lifshitz action. And what is also interesting is that you can apparently construct such actions even if you don't have Lorentzian metrics, because the basic building blocks of this boundary geometry are all degenerate metrics. But it's still good enough to define things like the extrinsic curvature, which is something like the Lie derivative along the velocity field of the spatial metric, so you can still define all these things. And this is some fourth order derivative term in terms of the spatial metric. And furthermore, in general, for Lifshitz theories, these are two central charges, so you have, in general, you have 2 instead of 1. But it turns out that in this model they are related. So if you compute these explicitly, you get this relation here, which is no surprise because it comes from the reduction. And of course, in 5 dimensions, you only have 1 central charge. Yeah. No, this is Z2. Okay. So now that we have identified all the sources and the vectors, you can make a simple counting argument. How many of them do we have? Do they match? And so let me take you through that. There are, in general, 15 components in all the sources, and there are 8 local symmetries. So these are diffeomorphisms, local tangent space transformations, gauge transformations, and isotropic Weil rescalings. And then there was this one constraint. So if you remove all that, you end up with 6 independent sources. And if you count how many vectors you have, there are 15 components, but now I have 9 ward identities, 8 because of these local symmetries. But there was this additional one, which corresponded to the fact that the Pfeffman-Graham expansion has an additional transformation symmetry which only acts at the leading order, but which allowed me to introduce another ward identity, so I can subtract 9 here. And so I get 6 again. So which is nice, you get 6 sources and 6 vectors. So you would think that then you're home free. But if you do the following exercise, you take the Pfeffman-Graham expansion in 5 dimensions, and you just trivially reduce that to 4, and you count how many free functions I have, you actually find that you have 1 more. So what happened is that this hatted T is the stress tensor in 5 dimensions, of the boundary stress tensor in 5 dimensions. And this particular contraction, this particular combination here, happens to just drop out of the ward identities and it starts to live its own life. So this is completely, this does not talk to the 4-dimensional sources and vectors anymore. So the 4-dimensional Pfeffman-Graham expansion contains an odd number of free parameters, which is a bit strange. Okay, so no, well, it's neither a source nor a vector actually.
Then how would you interpret it from the field theory point of view?
That's actually an open question, but it could be some kind of. So one thing that we should study is, for example, by looking at the phase space, taking the symplectic form of the phase space, you substitute in there the Pfeffman-Graham expansion, and you show that the symplectic product is diagonal in the sources and the vectors, and that this guy is not present there, and there would maybe some kind of super selection thing. But so for each choice of this function, you have a dual field theory. But what the real sort of, but this is sort of still very much an open issue. Okay, so well, I've presented a model which is a well-defined low-energy limit of type 2B string theory. I've identified the most general solution to the four-dimensional equations. Try to convince you that using frame fields you're able to identify the boundary geometry, which is in general torsional Newton-Cartan. These frame fields are also very useful. That was already known to compute the boundary stress energy tensor, and we do this for Z2 now. There are in general 6x6 sources and VEFs, and then there is this one additional free function that control the Pfeffer and Graham expansion. And this is still sort of to be interpreted. So to give you an outlook, so this was the nice thing of this model is that you get everything from the reduction. The not so nice thing about this model is it's very constrained. What you really would like to do is sort of a bottom-up approach. For example, take the massive vector model, which is sort of the minimal matter content that supports this type of solution, and then sort of do the same thing there. And it's very useful to have this case worked out, because then you can sort of now compare with the situation here. For example, it's not known whether you will find again such a free function. It's not clear what happens for different values of z, especially z larger than 2. The metric expansion in radial gauge, if you go beyond asymptotically locally Lifshitz, is completely obscure. It's highly non-trivial to compute it. It will involve lots of log terms. We don't really have good control here. You may even say that the natural gauge is not the radial gauge here. So there is an interesting question about holographic RG flow. These are all very much open questions. This model also happened to have a hyperscaling violating solution with these parameters here. So you could also look at that case. For phenomenological reasons, you may want to add charges. And finally, I'd like to mention that potential application here might be to the interesting work of Sun, which we heard about yesterday, which also involves Newton-Cartan. And this may be a natural framework to holographically realize such a scenario. Okay, thank you for your attention.
Comment first of all, in the massive vector model, at least for some values of z, the renormalization has been worked out. There is no extra free function, right? So
people have not imposed. Well, people have usually worked. So we asked, for example, the Amsterdam group, and they say for them it's not clear to them actually.
Well, I'm actually thinking of my own papers. So I'm thinking of papers published with my student over the summer. So we were analyzing Lifshitz in particular limits of z, but we certainly had no extra free function.
But this might be a feature of z equal to 2.
It could be.
It may very well be. It may very well be. So
I think it's more likely, if you ask me to give a guess, that the thing that you're identifying as a free function is actually a verb for an operator whose source you switched off.
Absolutely.
Yeah, and
Right.
the interpretation of that would come from the upstairs picture and is associated with scalars.
Yes.
And it's not, my guess is it's not there in the massive vector model. I mean, I agree the z equals 2 case because it's an integer value of z.
Mm-hmm.
It has some subtleties. I mean, our student hasn't entirely finished. But at this point, I don't see that you're actually going to get extra free functions there. So I would be looking...
So this is something we would definitely very much like to know the answer to. And I think that should be studied. And it would be very nice to understand sort of how universal these different models for Lifshitz are. It could be that in the massive vector model you don't have this extra free function. That may be a good asset of that model.
Just one comment. I mean, one interesting thing I think from the holographic perspective is that all top-down models we have can be understood in terms of deformations of relativistic conformal fixed points, with the exception of Jerome's very strange z, the very peculiar value one. All the others are now understood in terms of deformations. So you're doing one special kind of deformation. The cases we've been playing with, which are Ruth Gregory's cases, are also understood in terms of deformations. So, clearly they're universal in some sense. They have some interesting features.
Please.
I've also got a comment about hyperscaling validating geometries. I'm not so sure that they would always look like variations upon the Lifshitz holography that you could build up, because there's a whole range of values where what you see is that they actually look like solutions which are Ricci flat rather than Lifshitz or ADS. And so in that case, I don't think that the holographic dictionary would proceed anything at all like in ADS or in Lifshitz.
No, it was sort of I mean, the comment that I made is sort of a very crude observation, which is that they are just the hyperscaling solution itself is conformally Lifshitz. And you know that for ZH1, having a hyperscaling validation parameter is just something that is not upsetting the holographic normalization in any essential way.
Theta negative or theta positive, the usual intuition that you would draw.
But you have a case here where theta is positive. This comes from 5.
With the exception of this guy who can be related to ADS, but the rest really won't look like anything that has to do with ADS.
No, not with ADS, with Lifshitz.
No, not even Lifshitz. Really.
Well, they are conformally related to
This
Lifshitz.
really depends on the value taken by theta.
Oh, the details one has to work out, but I think that the real challenge in doing the holographic normalization lies in dealing with Z different from 1. I think that's the real challenge.
Any more things to be done? And thanks for the nice talk, Jelle.